Hello, welcome to this lecture on modeling, analysis and estimation of three-phase unbalanced power network. In the last lecture, we have been talking about the modeling of the three-phase transmission line, unbalanced transmission line. We are basically trying to find out the impedance matrix of a three-phase unbalanced transmission line, and then we ultimately seen that the impedance matrix of a three-phase unbalanced power transmission line is basically a symmetric impedance matrix. Now, let us try to find out that what are the expressions of all these elements. Now, as you can see that we have said that ZAA is equal to ZAB minus ZAD minus ZBD plus Z, no sorry, basically here as we can see that this particular expression of ZAA is nothing but Z bar AA minus 2ZAD plus ZDD, it should be 2ZAD, 2ZAD, sorry, AD. So, it is 2ZAD plus ZDD, and then also similarly ZAB as well as ZAC. So, then therefore, let us try to find out that what would be the final expression of, so ZAA. Now, ZAA is equal to Z bar A minus 2ZAD plus ZDD. Now, we said that ZAA is equal to that RA plus J omega k log twice S by DSA minus 1, right. I mean that is the expression. And ZDD we said that it is also RD plus J omega k log twice S by DSD minus 1, and ZAD is basically J omega k log twice S by DAD minus 1. So, now we will simply use these values. So, then therefore, from here I can say that ZAA is equal to RA plus J omega k log twice S by DSA minus 1, then minus 2 J omega k log twice S by DAD minus 1 plus RD plus J omega k log twice S by DSD minus 1, right. So, here I can write down it that it is RA plus RD. Now, here several things will go away. For example, J omega k terms will go away. So, then therefore, what it will simply remain is that plus J omega k log twice S by DSA plus twice S by DSD DSD minus log twice s by dAd whole square, right. So, this would be the case. So, it will turn out to be, therefore, ZAA is equal to RA plus RD plus j omega k log 4 square by dSA into dSD into dAd whole square by 4 square. So, it will be RA plus RD plus j omega k log dAd whole square by dSA into dSD. So, that would be the expression of ZAA. So, similarly I mean identically in the same way, if we proceed, so we will get that it is RB plus RD plus j omega k log say dBd whole square by dSB into dSD, and ZCC would be RC plus RD plus j omega k log dCD whole square by dSC into dSD. Right. So, these are the expressions of ZAA, ZBB, ZCC. So, basically these are the expressions of the diagonal elements of the Z. Basically these are the expressions of the diagonal elements of the impedance matrix. Now, let us look into the expressions of the off diagonal elements. So, the expression of the off diagonal element would be given by, so ZAB is Z bar AB minus ZBD minus ZAD plus ZDD. Okay. So, ZAB, right. Now, ZAB is equal to Z bar AB minus ZAD ZBD plus ZDD. Now, ZAB is basically nothing but j omega k log twice s by DAB minus 1. Sorry, this would be minus. This is minus. Minus ZAD would be j omega k log twice s by DAD minus 1. Then ZBD would be j omega k log twice s by DBD minus 1, and ZDD is plus RD plus j omega k log twice s by DSD minus 1. So, again j omega terms will cancel out with each other. So, what will remain is essentially RD plus j omega k, and the common would be log twice S by DAB minus log twice S by DAD minus log twice S by DBD plus log twice S by DSD. So that would be the expressions. So let us put some bracket if we wish. So then it will turn out to be ZAB would be given by RD plus J omega K log twice S into DAB into twice S into DSD. So it will be twice S into DAB into twice S into DSD, and then minus log twice S by DAD and DBD. DAD into twice S by DBD. So if we do it, it will turn out to be J omega K log DAD into DBD by DAB into DSD. Right? So it is DAD into DBD into DAB into DSD. So similarly, if I do ZBC, so you see, so when it is AB, so it becomes AD, BD, AB, DSD. So then similarly, if I do ZBC would be given by, if I do it, J omega K into log DBD into DCD by DBC into DSD, and ZCA is equal to RD plus J omega K log DAD into DCD by DCA into DSD. So here one interesting fact is that here the mutual impedances also have some resistive component. So here the mutual impedances also have some resistive component. So that is very interesting observation. Mutual impedances also has resistive component. And this component and this resistive component is actually appearing due to the effect of the fictitious conductor ZDD, and as we know that this fictitious conductor ZDD essentially represents the ground effect. So then therefore, RD is basically nothing but the ground resistance. So then therefore this mutual impedance has also some resistive component. So then therefore as a result we can see here, so then therefore this symmetric impedance matrix, all the elements has got their resistive component as well as the inductive component, correct. And for the diagonal terms, and this resistive component is due to effect of ground and the diagonal elements also have this is also have resistive component and this is due to effect of ground plus the conductor resistance. So this is an interesting observation, that is essentially all the elements have got their resistive component. For the diagonal terms, the resistive component appears due to two effects. One effect is basically due to the ground and also another is due to the individual resistance of the conductor. But for the mutual impedance, the resistive component comes only due to the effect of the ground. Now what happens is that usually the distance of this fictitious conductor is a very deep into the ground. So then therefore the distance of these conductors, for example suppose even that I have got three conductors, phase A, phase B and phase C. So this is DAB and suppose my fictitious conductor is somewhere here, DD dash. Now if this distance is very large, suppose this distance is say D, capital D, suppose this distance is capital D and suppose these distances are L and this is basically a kind of equilateral triangle. So this is also L, this is also L, and then we have actually that so now let us say that this is DCD say, and let us say that this is BDBD and let us say that this is DAD. So this would be DAD, this is DAD obviously. Now if capital D is much less than L, if this value of capital D is much greater than L, so then obviously I can say that effectively DAD is almost equal to DBD is almost equal to DCD, right. So then therefore suppose if I say that these values is denoted as DE, so then therefore all these expressions I can say that ZAA would be given by, so ZAA I can say that it is given by, I can simply write it here that ZAA would be given by RA plus Rd plus j omega k log dE by dSA dsD, right? This is wrong. So if I say that this is root d, if I just define it that this is root over d, so then therefore dAd square would be d. Similarly, this would be given by Rb plus Rd plus j omega k log dE by dsB into dsD, and this ZCC becomes Rc plus Rd plus j omega k log dE by dsC into dsD, that I will get. And what happens to ZAB? ZAB also becomes DAD into DBD, because these two are both are almost equal to root over DE. So then therefore this quantity is also DE. So then therefore I can say that ZAB is equal to RD plus j omega k log dE by DAD, and it is DAB by DSD. So it is DAB by DSD. Similarly, ZBC is given by RD plus j omega k log dE by dBc into dsD, and ZCA is equal to ZAC is RD plus j omega k log dE by dCA into dsD. So these are the final expressions, right? So that would be the case. Now here, as we have already said, in the case of the single phase transmission line, this quantity DSD is nothing but 0.7789 into a radius of the fictitious conductor d dash. Now because it is a fictitious conductor, so then therefore we can always assume its radius. So then therefore, as we have already done for the case of the single phase transmission line, in that case we have already assumed that we will keep the value of dsd is equal to 1. So then therefore in this case also we will assume that my dsd is always equal to 1, right. So then therefore all these expressions, so then therefore for example ZAB would be is equal to RD plus j omega k into dE by DAB, ZBC would be equal to RD plus j omega k into log dE by DBC, and ZCA would be equal to RD plus j omega k log dE by DCA, and ZAA would be equal to RA plus RD plus j omega k by dE by DSA, and similarly, right. So then in all these expressions DSD would be taken as 1, because it is a fictitious conductor. Now let us, so then therefore by this we are now able to find out all the elements of this symmetric impedance matrix in terms of the dimensions of the line. Now to appreciate the application or rather the use of all these expressions, let us take an example. So, let us take an example. So, example is that I do have three conductors A, B, C, phase A, phase B, phase C. The distance between phase A and phase B is 10 feet. The distance between phase B and phase C is also 10 feet. So, then obviously, the distance between phase A and phase C would be 20 feet. And then I do have somewhere here the ground wire, and this distance is, let us say, 15 feet, and I do have somewhere here ground, actual ground. Let us say that this distance is 45 feet. Now, some data are given. The data are given as that the radius RA is equal to RB, sorry, this is the resistances. RA is equal to RB plus RC is equal to 0.278 ohm per mile. These are the resistances. And then, so then therefore, from this we can calculate that what would be the DSA, DSB and DSC. So, then therefore, and also the values of DSA, DSB and DSC, they are given as that 0.01668 feet, right. So, please note that these are the resistances. So, these are the resistances, and these are the radius, right. And let us say my RD, that is the ground resistance, is given by 0.09528 ohm per mile, and my DE, now these values are already known from some experiment. So, these values DE is known as 2790 feet. Now, essentially there is a table already available in that book, what I have already mentioned. So, in that book, for different types of ground, the effective value of DE has been given. So, then therefore, this value has been taken from that particular table given in that book. And then we have to calculate the value of ohm, and my frequency is 2 into pi into f, that is, and f is equal to 60 hertz, right. So, this is one line, and now we would like to find out that what would be the impedance matrix of this line, right. So, then therefore, we will solve this example in the next lecture. Thank you.